That I have a pond of water and it's not a windy day, there's no current, and I throw a rock into the pond right there. Well, what we would notice is a few moments later is that we would have, and I didn't get it quite in the center, we would have a wave happen a few moments later. And what would happen is that wave would continue to move outward, and we'd have wave after wave, crests and troughs would continue to move from that spot. And we can recreate this in the classroom, but we've got, we would call this a ripple tank. But you would see these waves moving out from the center. We could also have the exact same thing happen. Let's say I've got a motorboat or a boat out in the lake. And what happens is that after a certain period of time, what we would anticipate is that there would be this similar ripple. But the question is, what if my boat was moving? Well, what would happen is that the rings would be moving with an initial velocity. And what we end up with is a scenario that looks a little bit like this, where if we were moving in this direction, the distance the wave has traveled will appear to be a little bit less. And this is referred to as the Doppler effect. So we've got some kind of velocity of the wave, and we also have the velocity of the object. And we need to take both of those into account. Where the waves are close together, we know that that has a certain meaning. And where the waves are close together, this is going to be, let me just write close together. This is going to have a higher frequency of waves approaching me. And on this side over here, I'll just do it a different color. This will have a lower frequency, far apart. Now, these are water waves that I was referring to in this case. Start. Let's work through some examples here of how we can determine the speed of our boat. So once again, we have a boat here moving in a direction. And what person A and what person B are going to see is very different. The frequency that person A or B observes, and I'll put A or B here, depends which one we're talking about. The frequency of person A or B is equal to the frequency of the object multiplied by, and it's the speed of the wave divided by the speed of the wave plus or minus the speed of the object. So let's think about it from person A's perspective. This is getting bigger. And because that's getting bigger, we're going to use the add sign in our formula. From the perspective of person B, this distance between waves here is getting smaller. And so what we'll do is we'll use the subtract part of our formula. So we have a boat, and the boat is our object, and it's moving at 5 meters per second, and it's moving to the right. We have our wave, And our wave is moving at 10 meters per second. And remember, the wave is moving outward. It's moving in every direction in our lake. And then we also have the frequency of the object. The object has one wave every 2 seconds. And let's keep that in mind. That's 0.5 hertz. That's a frequency. So we're seeing a wave every 2 seconds. We can use our formula and determine what we would recognize. So person A, the frequency of person A would be equal to the frequency of the object times the speed of the wave divided by the speed of the wave. And because person A, they're getting further apart, we're going to add these together and we're going to get the speed of the object. Okay. And while I'm at it, I'm just going to do the same thing. I'm going to say, well, the speed that person B is going to see is the speed of the object times the speed of the wave divided by the speed of the wave, subtract the speed of the object. Okay, so they're going to see two very different scenarios. All right, let's calculate those. So what we have here is we have speed that person A, or the frequency person A is going to observe, is 1 over 2. That's, one wave every 2 seconds. And the speed of the wave, I think the wave was 10 meters per second. And then we're going to have down here 10 meters per second take away, plus 5 meters per second. So let's see, the frequency is going to be 1 times 10, so that's 10, divided by 2, and then this is going to be 15 here. So the frequency person A is going to see it. That's 10 over 30. How about 1/3? And let's look at the units. Here I have meters per second, and then in brackets here I have, there we go. In brackets I have meters per second, and there I have seconds. So with my units, what we're going to observe here is that the meters per second is going to cancel the meters per second. I'm left with seconds on the bottom, which is frequency. So we are going to see one wave every 3 seconds. One wave every 3 seconds. Okay? Or once again, our frequency is 0.3 hertz. Okay. What about a person B? And we're anticipating that they are going to see waves more often because they're coming in, they're pretty close together. Okay, so frequency of B would be one wave every 2 seconds. And then we've got 10 meters per second divided by 10 meters per second, take away 5 meters per second. So frequency at A would be 1 times 10 again. That's 10 meters per second divided by, on the bottom, I'm going to have 2 seconds times 5 meters per second. So here I'm going to have 10 divided by 10. So the answer is going to be 1. And let's just look at our units here. Meters per second, meters per second. I'm left with seconds on the bottom. I'm going to have one wave every 1 second. Okay, so I'm going to have one wave every 1 second. The frequency here is 1 hertz. So far in this scenario with the Doppler effect, we've looked at what happens when the boat is moving at a speed less than the speed of the waves. And let's think about what that means. So right now, person A is only seeing a wave, in the last example, every 3 seconds. That's not so bad. Person one, on the other hand, is getting a wave every second. And that's a lot of water coming at them. But what happens when the boat speeds up? Let's look at some very specific examples. So now what I have is I have a boat um, moving at the same speed as the wave. Okay, what we see here is we see that the wave speed is 10 and the boat speed is also 10. And what happens is that the boat is now moving and you would see it here as opposed to there. And so what happens is that all these waves here are all combined. So when person B experiences these waves, they're going to all hit at one time. Okay, person A is still going to see these waves happening every once in a while. I think it's going to be probably even less frequent than before. And you could calculate it with the formula we did previously. But person B is going to be, let's say person B is sort of right in here. All these waves are going to hit at one time and you're going to get really splashed. A lot of water is going to come at you all at once. Okay, let's call it the big splash here. Okay. Then what we have is what happens if the wave is moving at 10, but the boat is actually going faster. Okay. So what's happening here is that the boat, instead of being right there, the boat is moving faster than the wave. So what's going to happen is B is still going to get the big splash, but the splash won't happen until after the boat has passed them. And we can figure out how long after, we can do some speed calculations. But the wave of the water that's coming right in here, this big wave that's going to come from the speed of the boat and the waves created, this is going to come after the boat has passed. And that is a very, very specific situation. Let's look at three scenarios here. And this applies to the water waves we've already done, the sound waves I'm going to talk about now, or even the speed or the movement of light, which we're going to get to shortly. In the first scenario, we have an object. I've got the object here in red. So let's say it's an airplane. And it's moving slower than the speed of sound. We get a person here on the ground. And what would they observe? Well, they would see as this wave approaches them, they're going to hear right here, they're going to hear this black curve here that is the sound wave. They're going to hear the airplane. The airplane's not there yet. Remember, the airplane's red, so they're not going to. The airplane's going to be above them right here, but they're going to hear the airplane before the airplane arrives, and it's going to be a higher frequency. After the airplane passes them, the waves are further apart. It's going to be a lower frequency. Once again, that's the Doppler effect. Our second scenario is that the airplane here in red is going at the speed of sound. So it is right at the crest of these waves that are all packed together. And what's going to happen is just as the airplane passes that person at point B, all the waves, and this is significant, all the waves are going to hit at once. When it was a water wave, what we saw was they got splashed. But in sound waves, you're going to hear a big boom. And this is called a sonic boom. And it's going to happen at the exact moment that the airplane is at the same place as the person. In scenario 3, what's going to happen is The object, the airplane, is out in front of the sound wave, so it's supersonic, or its Mach number is greater than a Mach 1, because this one here, scenario 2 is Mach 1. This is faster than the speed of sound. So what we're gonna see is as the airplane, that's the red dot, reaches the person, which is the green dot, you still haven't heard anything. Nothing at all. It's not until the airplane has passed you by possibly seconds, boom, the sonic boom happens after the fact. Okay? So you're going to get the boom, but the difference between the two situations is this one is a delayed boom. And next, what we're going to do is we're going to look at how to calculate the distance between when the boom happens. Okay, so very, very briefly, when the object is going slower than the speed of sound, we see a Doppler effect. We got higher frequency here, we got lower frequency over there. When the object is moving at Mach 1 or the same speed as sound, you're going to get hit with all the waves at once. Water waves, you're going to get a big splash, but sound waves, you're going to get this big boom at that exact moment. And scenario 3, when your airplane is moving faster than the speed of sound, you're going to get the sonic boom, but it comes later. Start. What we know is that as an aircraft flies supersonic speed, so an example here is we got Mach 2 going on. So it's at double the speed of sound. So it's going to have a delayed sound wave for its sonic boom. And there's a cone shape in behind the airplane of where the sound waves are traveling. So it's a cone shape. So I can look at, hopefully you can see there's a little faint green line here. I can figure out what this angle here is. Okay, that angle. And it's quite simple. It's related to the sine curve. And so what we know is that the angle, so the sine of the angle is equal to the speed of the sound divided by the speed of the object. In this case, I'm going to put airplane. Okay, so the sine of that angle equals the sound divided by the plane speed. Okay, so I've got Mach 2 going on. So let's see if we can figure this one out. So let's see. We're going to say that sine theta is equal to the speed of sound. And I don't know what the speed of sound is. It depends upon the temperature. But it's going to just be, I'll just call it the speed of sound. But what I do know in this particular example, if you knew the actual values, you could put it in. But Mach 2 is 2 times the speed of sound. And so what we have here is I've got the speed of sound divided by the speed of sound. So what I have here is I have that the sine of theta is 1 over 2 because we've got the 2 right there. Okay? So the sine of theta equals 1 over 2. And what would that be? Ooh, I don't need to write sine in it again. It would be theta is 30 degrees. Okay, so I know in this particular example, and the faster the airplane's going, the more narrow the cone becomes. But I know that this is 30 degrees. Okay, now what I can do is using the height of my airplane, okay, so I know this right here. I can figure out this right here using my angle. And so I'm going to draw that triangle down here. So what I know is that this is 30. I know that it was 1,000 meters high. We have a right angle here. This looks like my adjacent side. This looks like my opposite side. And I know that the opposite over the adjacent is the tan of my angle. So I would be able to go 1,000 meters divided by the tangent of 30 degrees equals my adjacent. And I'm going to get a calculation that my adjacent is 1,732 meters. What does this mean? This means that the airplane is going to be 1,732 meters past me before I hear the sonic boom. Now I could use the speed of sound and figure out how many seconds that is. I'm going to guess at Mach 2. That's going to be, it's going to be a couple seconds away.